characteristics of the Lunokhod 1 and Yutu rover landing sites, and WD Mare Imbrium on the map.
Good afternoon. This is a joint work of 3 countries. It is, of course, Russia, it is, of course, the United States, and it is China. And so we try to consider all data, all results taken in the Lunokhod 1 area, new results in Yutu area, and they are very close according to space scales, only 500 kilometers across, and they are both in Mare Imbrium, close to Symposium. This is Lunokhod. It is Lunokhod 1, and this is lander, and this is the route. You landed here, then went to this, come back to here when this image was taken, and this going to here, entering this crater border, and so on. And I would like to pay your attention on the names. Names of small craters here. These are names of the members of the Lunokhod crew or Lunokhod team, and the only Boris Nipoklonov. He was scientific leader of all the mission, but he was very close to the crew, so his name is here. So this is typical landscape in the area of studied by Lunokhod 1, and this is some mountains on the horizon. It's Promontorium Hercules, and we have, as in most places on the moon, we have craters which are morphologically prominent, less prominent, what Natasha Kozlova showed you earlier, and since that Lunokhod 1 times the studies, we now understand how long craters can survive on the surface of the moon. For example, that big crater Bora, it can stay several hundred million years. Its age, and we're making more mature, it can last another 1 or 2 billion years. But small craters, they are only several tens of million years. So this is just examples. It's fresh crater, A, B, B, and this is we are here crater Borea, and we are somewhere here. We look inside. We see interiors. We are on the rim. You see, it's not a lot. It's not very many rock fragments. But if we look inside, we enter a little bit inside. It's much more rock fragments, partly because of formation of new craters, but mostly because of overturn of regolith in the process of downslope movement. And we understand why on the rim of the crater of this crater Borea, it's not a lot of rock fragments. Recently we studied how long can survive rock fragments on the surface of the moon if they are on relatively flat, horizontal surfaces, and we see that for if some amount, a lot of them, and then smaller amount, and within a few 100 million years, they almost all are destroyed. And this is some formal classification according to primary shapes of the rocks and degree of degradation, something like this. Eventually you come something like this. And this is good for description, but sometimes when we pay attention on the morphology of rock fragments, we may notice something interesting. For example, this is very unusual rock fragment, and Lunokhod, say, stepped on it or so, and it was even part chipped off. But this is something not typical, and this, we believe, is this rock fragment came from some basalts which are below its calendar jointing. It's quite usual things. It only demands that the thickness of lava flow should be large enough. It's tens of meters more. And this is just to show you a regolith. And when it was turned, this is a panorama taken with horizontal scanning, axis of scanning, and it is behind, it's forward, and when we change, it's like shear. We see here the shear is quite smooth, but when this wheel is pushing to here, we form clods. It says something about how cohesive is the Lunokhod, the lunar soil. And this is Lander. It is Lander, Chinese Lander, and Chinese Rover. It landed in some place. It is, as in Chinese publication, it is so-called C1 crater, and here is small C2 crater. They landed here and then traveled this way. For some reason, it's not said very clearly in the official publications. Its wave was only 114 meters, but it made a lot of interesting observations. And what is important, when it was landing here, it was like hovering over the surface and tasting how rough the surface is below, and after a while, when it was some evidence that it's rather smooth, it is landed. It's not landed here, it's landed in here. Again, it's not clear, at least for me, what was a capability for this selection. Was it what is a resource? It can move for tens of meters or hundreds of meters. For example, I don't know if, because of course the landing ellipse was like this, and it could come to here. It's not understandable for me. Can it get out from the crater? Which certainly is dangerous, and or not. So in this case, it's probably also is factor of light, which is also a very important factor. So it is the area of landing. It is C1 crater with a lot of rocks on inner slopes. It's part of the big cluster of rocks. And it is C2 crater, and you see different, it's a prominent crater, it's much more mature small craters. So generally it's practically the same, and this also practically the same situation like in Lunokhod 1 area. And similarity extends also to this thing. You see this very unusual rock fragment. We believe it's again something which came from the part of basalts with columnar jointing. Interesting that the depth from which this fragment came, what is on this surface here, is came from the depth of 40 to 50 meters. Same case like in crater Boyer. And later I'll show you on some where some vertical section could be. So this is the largest boulder studied here, and we see here this is microcraters, very similar to what is on the lunar samples brought by Apollo astronauts back to Earth. And Lunokhod 1 had so-called probe, this device to measure physical-mechanical properties of regolith, and it collected a lot of interesting data. We now know strength and compression and shear, and also we know dependence of these parameters on the angle of surface inclination. On steep surfaces or moderately steep surfaces, regolith is much more friable, much weaker. And this is Yutu traces. They didn't have the device to measure physical-mechanical properties, but you see the traces look very similar. We can say probably physical-mechanical properties are also very similar. So general conclusions. The geologies of Lunokhod 1 and Yutu sites are very similar. In both these sites, there were observed rock fragments suggesting that their source rocks at the depth of 40 to 50 meters have columnar jointing. Yutu had a ground-penetrating radar, and it showed multi-layer structure of the regolith. It's expected, it's just, it should be so, but we just may suggest this, we may propose it, but now it is measured. And compositions of surface materials measured by the instruments on board of Lunokhod and Yutu, they showed some difference with what was measured from above, from the orbit. It's partly due to low measurement accuracies, but maybe also it's due to real differences. We discussed what kind of lessons we can extract from these two missions. And first of all, we think it is necessary, and it is already planned by ESA, that we should, in future missions, to use terrain recognition equipment and software to hover over the surface and to land in more or less safe place. We suggest to use ground-penetrating radar. And look, here is it's like section, it's 700 meters. Here are rocks, basalt spheres with columnar jointing, and these are some layering, rough, of course, measurements, but they're good, of layering within the regolith. It's necessary to use a robotic arm which should carry instruments It was on Yutu, and the best one up to now is Curiosity. And we suggest that in many cases we should not drill. We should use some knowledge of cratering mechanics. If we have some crater formed, here we should have what is on the largest depth, here we have what was on the surface, and just studying radially around the craters, we may penetrate down to 1/10 of the crater diameter. So, a few hundred meters. Thank you.